Pi-Al based for here. If it makes sense, it makes sense. What I'm trying to do is create a series of training videos on IAQ. And I will try to keep each one of them very short, compact, and to the point. In this case here, we're looking at determining the cooling capacity using psychrometrics of a unit. I hate to say this, but it wasn't until about 15 to 20 years ago that I even knew what the word psychrometrics meant. And then it was just a few years after that, I met a young man that actually taught me so much about psychrometrics. It made me so interested in pursuing it as a service tool. Most everybody in this industry never uses psychrometrics and doesn't understand what it pertains to. But it's basically the thermodynamics or the science of air. In other words, the moisture and the vapor content in the air. So what we're doing here is this scenario is actually a true scenario. And it's going to address one single package unit. There happen to have been two of them on this facility that we were looking at. We'll go over formulas and how to proceed through the formulas, the conclusion, the issues that were actually found and corrected, and the final outcome of this one video. You must understand that you can use this on any unit that there is. And during one of my training sessions, it was in a room, and the guys actually took a little handheld barometer and took the temperature differences, and come to find out we had a 3-ton unit and we were actually producing 33,000 BTUs. It's kind of interesting to see what's happening, where it's happening. This was a 20-ton package unit with dual circuits, actual unit. The company I was working with at the time was called to a hotel that indicated a need to add a package unit to the existing ballroom. When asked why, they couldn't tell us other than competing companies indicated the need for the unit. When asked what had changed, basically nothing had changed. And a matter of fact, they'd done some reduction in lighting load through adding by adding electronic ballasts and T12 lights. We suggested letting us test the unit and then come up with the suggestions. There were 2 units. This is one. And this one was the better of the two, believe it or not. These are psychrometric calculations for technicians. I don't want to get into all of it, but the one we're going to be using is the total BTUs down at the bottom. And you don't need to know all this. All you need to know is the 4.5 for total, 0.68 for latent, and 1.08 for sensible capacity. That's all you need to know at this time. Total capacity of a system is obtained by measuring the CFMs, dry bulb, wet bulb, entering air, discharge air from evaporated, which normally is saturated. And the formula is the CFMs times 4.5 times the difference in enthalpy gives you your BTUs, or gives you your capacity of that unit. We're only going to be using this one. There will be other videos showing you and how to use for gaining the sensible capacity, or gaining the latent or the moisture capacity of the unit, what it can remove. And all that will be discussed in later videos. Determine the capacity of a system. The system's a 20-ton roof-mounted package unit. Upon checking the unit, the following was found. Airflow was checked, and we had no outdoor air, and it was at 6,300 CFMs. The no outdoor air was a concern to me because building pressurization and all this other, and wasn't for sure on the ductwork sizing, but sometimes the ductwork sizing takes into consideration you're bringing in a certain amount of outdoor air, so your return may be a little bit smaller than what needs to be. Condition of the return air was 78-degree dry bulb, 65-degree wet bulb. Condition of supply air was 66-degree dry bulb, 58-degree wet bulb. On a psychrometric chart, these are the 2 points that are found on this particular chart. Or more importantly, what we're going to be looking at here is the enthalpy In other words, the BTUs per pound, which happened to be on the entering point with 29.9 and on the exiting or the supply 25. Now that shows a 4.9 BTU per pound difference. And right there off the bat, I understand that there's an issue. And the reason I understand that there's an issue to maintain what we want to do, that difference should be 6.667 pounds, BTU per pound. There it's 4.9. So we already know there's an issue there. Another reason I know there's an issue is the dry bulb. The dry bulb goes from 78 to 66. We are taught as technicians that we need to have an 18 to 22 degree drop across the coil. In this case, we only have 12 degrees. So we're not even reaching dew point. If you notice down below, dew point is well down there on what we're trying to do. In the case where we'd be trying to do, let's say that we are looking at a 70 degree area or 70 degree, 50% RH in this area. That means our dew point needed to be 50 degrees. So we're not even close on any of this. So what did we do? First, we found the enthalpy of the first point, which happens to be 29.9. You've seen it on that screen. Second, we find the enthalpy of the second point, which is 25. Difference between those two is 4.9. So we got to put it into the calculation. We know the CFMs are 6,300. We know the enthalpy of each point is 29.9 minus 25. So what that gives us is 6,300 times 4.5 is 28,350 times 4.9 or 138,915 BTUs calculated for this. That's only 11.5 tons. We got an issue. What happened? Where did we lose capacity at? Now, discussion on this could go a long ways. And if we actually have a live presentation, what would be discussed? Well, we found the reason for the cooling issue was not something new, but something old. We found the manager didn't believe in maintaining or maintenance of the unit. Manager was with us during the entire testing, both before and after, and we instituted the corrections. We had a whole list of issues we found during the investigation. The unit was dual circuit. Next slide will detail all the issues. What I'm getting to is this, is that if somebody doesn't believe in maintenance, here you go. Now, what I didn't put in here was what the outdoor temperature was and what kind of effects it had. There's a lot of the different effects that has it on there. All we were trying to do was measure what was going on with that unit at that particular time. It's much like a doctor does with a screenshot on your labs that they take. We were doing just a screenshot of what was happening and trying to find out why it was happening. Issues listed, both the condenser and evaporator coils were dirty. Now, you couldn't see the dirt because somebody got it off the surface, but they were embedded. The coils were completely embedded. And it didn't really show on gauges because somebody had played with the charges so much that it didn't show. The configuration of coils had dirt trapped between the two coils, two circuits. Remember, we had dual circuits. Belts need adjusted. And with the coil issue, airflow was increased. Just by cleaning the evaporator coil, we increased the airflow significantly. And then we adjusted the belts to what we believed was a design of 400 CFMs per ton. Refrigerant charge in the first circuit was overcharged. Yeah, because they were trying to raise that saturated suction temperature. And we had to remove, the removal of the excessive refrigerant was completed. As a matter of fact, some of that excessive refrigerant was put in the second circuit after we found a leak and repaired the leak. That second circuit was low enough that it was operating off its low pressure controller. It wasn't because it was staging on. It was operating off the low pressure. And so we removed the refrigerant for first, added second, leak was found and repaired. Economizer engaged and hooked up. We was shut off, thinking that would help. That doesn't help. In areas where there's high RH or high moisture and humidity is an issue, Shutting off the economizer can put the building into a negative because of bathroom exhaust and different exhausts going on in the building. And now you have no chance of bringing any of that outdoor air through a conditioned coil. So shutting it off was actually detrimental to the humidity issues within the building. And this was just part of what we was doing. Matter of fact, we did all this to both units. Final results. We went through the measurements of the unit a second time with CFMs and all information collected at the exact same location. Remember, we had 2 units not working correctly. This one was in better shape than the other one. The actual other one was somewhere around 9 tons of capacity on a 20-ton unit. We ended up with the unit doing 19.2 tons after we adjusted it, after just above 11 tons. We gained, you're not going to get to 100%. There's weakness within there. We considered this to be exceptional for what it was doing. The other unit, not mentioning this, was doing just under 9 tons. We ended up bringing it up to right about 19 right at 19 tons. After completing the same thing on it, we ended up doing a little over 19 tons. Of the total 40 tons possible, we ended up with 38 tons of cooling, and the building was comfortable. The area, the ballroom was comfortable. There was no need for an additional unit. What happened was the manager did pay us. He signed a maintenance contract and now sees the value in maintenance. Seeing is believing. This is something that you as technicians can utilize. You only need something that will measure wet bulb, dry bulb, or what's coming in the airstream, a handheld velometer, or something you can measure your airflow with or calculate it with, and you can move on from there. With all that said, that's the end of this video. Again, these are going to be short, to the point videos. I'll be adding other videos pertaining to psychrometrics and indoor air quality. There will also be added videos pertaining to the RCCD control valve, which could have been used in this situation, ionization, the proper application, location, and what ionization can do and can't do. There will be a series of videos, and I hope to be adding many more in the upcoming months. Thank you, and bye.